block some light. So if some of our supernova light was blocked, and we didn't know that, then we would get the wrong distance for it, and we'd get the wrong Hubble constant. Okay. So that's something we have to worry about, and how can we check that? Well, here's actually a really cool picture of one of these dark clouds in the Milky Way, which is full of these interstellar particles that are blocking the light. Okay? So that's not a place where there are no stars. That's a cloud of gas and dust in the Milky Way, which is blocking the light from behind it. And the way you know that is if you look at the cloud in optical light, it looks dark. But if you move to longer wavelength light, which doesn't get blocked as much by this interstellar dust, in infrared light, you can see the stars starting to shine through. So what we did for the supernovae is instead of measuring optical images like you see here, visible light, we tried to make the measurement only using infrared light, so we wouldn't get affected by this dust. So that was this paper I wrote with a postdoc who's now in Stockholm and a researcher in Germany, in Munich, okay, that just came out this year. And our answer was this one here. So here is the original answer using optical light. Here's the answer using infrared light, and you can see they agree. So we didn't move all the way over here to fix the problem. All right, so I've probably gone way over time, but let me just summarize. So these type 1a supernovae are excellent standard candles, or we call them standardizable because they're not all the same. We have to make a few corrections. Okay? But we use those to measure distances across the universe. Okay? When we combine them with geometric techniques like parallax and Cepheid variables, we can measure the Hubble constant in a nearby universe. And our answer is about 73 plus or minus 2. That's about a 3% uncertainty. And our value differs from the best result from the cosmic microwave background that we'll just hear about by about 9%. Okay, so that 9% is bigger than 3%, so that's the issue, right? We think we're making a measurement that's good to 3%, and we're off from somebody else's answer by 9%. So what's going on? So either we or the CMB results or both are mistaken, or the very exciting possibility is that we might have found a clue that there's more to the universe than we already know. Okay, thanks.
Questions for Professor John. We'll have time for more questions during the panel discussion. But if anyone wants to ask something now. Okay, Danny.
When you look at a star that looks like it's in the galaxy, how do you know it's in the galaxy and it's not somewhere behind it or somewhere in front of it?
That's a good question. So the way we really test that is that these galaxies are really far away, so it's unlikely it's a regular star. It would have to be, is that supernova maybe behind the galaxy that we think it's in? And so the way we test that is we take a redshift measurement of the galaxy using light that's coming from the galaxy itself. And then we look at the redshift of the supernova and we make sure those match. And that tells us that it has to be in the same galaxy.
The 2004 gravitational lens measurement, the Hubble constant.
Yeah.
I noticed that was significantly below.
Yeah, let me see.
I think it was gravitational under.
Too many innovations. So. This one that you use? Is that what you're
No, not the lasers. From the graph that has the Hubble measurements in my daughter's life at 96.
Oh, okay. Let me. This one.
Yeah. The 2004.
Yeah.
That one.
Yeah.
That one looks like it's significantly below everything
Right.
else.
You can see what the error bars were like in that time, right? So this is like 40 plus or minus 20. So it's actually not that far from 70. It's like only a 1.5 sigma result. So yeah, I don't know what was going on with this. I don't know what paper this is, but yeah, 40 is sort of adequate. It's kind of almost as bad as 550 at this point.
Actually, two remain. You mentioned before about the distances, right? Not the measure. Does the size of the star matter in terms of establishing how far away?
Yeah, so if we can measure the physical size and the angular size of the star, then we could use that also to tell the distance. But it turns out that the stars, even their physical size is too small for us to be able to resolve that. There's just all the stars are just really so far away. They basically just look like points of light. So they don't have a different size when we take it. Any size that you see in the image is actually just from the telescope itself blurring into the light or the Earth's atmosphere.
Less than a pixel.
Yeah, right. Yeah.
Okay, maybe just one more, and then we'll save them for the panel discussion. Back there.
Couldn't we use a Hertzsprung-Russell diagram to determine the apparent size or the mass of the star?
Yeah, that's right. So if we go back to that first image I showed of the Orion, if you really wanted to measure distances just looking at that image, you could put those points onto a Hertzsprung-Russell diagram and figure out, okay, I know the temperature of this star, then I might know its distance. But actually, if you just know its temperature from its color, for example, you might not know if it's a white dwarf, or a main sequence star, or a giant star, and those would all have very different distances. So in fact, one thing, if you look at, I encourage you to Google this, but Gaia took its distances and made a beautiful Hertzsprung-Russell diagram with the real distances. So go Google that. It's an amazing video showing them putting that HR diagram together. But it really helps to have the distance before you make the HR.
Yes.
Okay, let's move on, and then you can ask more questions later. So our next speaker is going to be Maha Bacharil. He's going to tell us about an alternative method of measuring the Hubble constant using the cosmic microwave background radiation.
Hi everyone, Matt Magosha here. You kept hearing about the CMB, so I'm going to explain what the CMB is and how we measure it and how we can get the expansion rate of the universe from it. Okay, so the thing I want to remind you from the previous two talks is that in order to measure what the expansion rate of the universe is, you need two things. You need a distance and you need a redshift. And Saurabh and Steve already explained what redshift is. You can think of it as expansion of the space. The space is expanding and the photons of the light get stretched out. So because the light gets stretched out, it looks redder. And so if you can measure an object and see how red its light has been stretched out, then you can get its redshift. And if you can also measure its distance, then you can connect the two and get the expansion rate. Okay? What Saurabh has talked about so far, and Matt will talk about in the next talk, is stuff that, there we go. Okay, so stuff that happens very late in the universe, and that's why he used the phrase local. This diagram is showing you a rough, brief history of what happened in the universe. There's a lot of stuff happening here. It's very condensed. But it's important to understand this brief history really quickly in order to place it, get the context of what we are going to be measuring with CMB. So we think there was a big bang in the beginning of the universe. The universe was very hot and very dense in the beginning. And then the universe expanded, and because it's expanding, the stuff in it cooled down. And eventually, it started condensing under gravity and forming things like stars and galaxies. And eventually, you get all these galaxies which have supernovae, etc. And then the distances and redshifts that you usually measure, the local measurements of H0 come from late in the universe. Right? And because the speed of light is finite, because it takes time for light to travel, things that you measure nearby are also things that you're seeing the light from more recently. What would happen if you went all the way back, very close to the beginning of the universe, and the universe is very hot and dense? That's where you'll see this thing called a CMB, which I'm going to explain. Right? So where does this come from? And if you can understand where that comes from, can we get a distance and a redshift for that ancient light from the beginning of the universe, and then use that to measure an inferred expansion rate, not locally, but far away and very distant in time. So 13.5 billion years ago, roughly, right? We think that because the universe is expanding, that means that it was very hot and very dense in the past. It was very hot and dense. We think there's a time when the temperature was so hot, around 3,000 Kelvin or 5,000 Fahrenheit, that all of the stuff in the universe, there were no stars. Everything was ionized. Everything was an ionized gas, like a plasma. And you can see that the things that are bouncing around here, the yellow stuff are photons. This is very hot and dense. There's lots of light. Then you have the ionized parts of the atom, right? So you have the proton. Most of the universe is hydrogen, and you have protons, and then you have the electrons, and together that they form a hydrogen atom. But as the universe expanded, this gas cooled down, and the electrons got captured by the proton and formed a neutral hydrogen atom. And when that happens, the universe goes from the state from when it was hot and opaque to cooler and transparent. And then these photons become free and they freely travel. So at this epoch in the universe is very hot and dense, you have this light emitted, and that light freely travels without interfering with anything late in the universe. And then eventually it gets stretched out and stretched out because of the expansion. And this is what we call cosmological redshift. So that's stretching out of the light. And then we end up measuring that eventually. So if you started out with light that was extremely high, high frequency, short wavelength, you've seen the electromagnetic spectrum, somewhere out here in the visible or the infrared spectrum, then this stuff gets stretched out and eventually we measure in the microwave. So here's an animation that shows what I was talking about. Initially, in the beginning of the universe, everything was hot and dense, everything was ionized, and then it cooled down, and the photons became free. This is a schematic depiction of a photon that's traveling. It's no longer interacting with stuff. And then as it's traveling, it's traveling for billions and billions of years. It doesn't get disturbed by anything. And then you can see that it goes from blue to green, and eventually it's getting redshifted. And as it travels, the universe is evolving. Stars form, galaxies form. And it gets redder and redder, and maybe eventually it might encounter something in between. But it keeps traveling for billions of years. It started out 13.5 billion years ago, gets redder and redder and redder. And there's many of these photons, but this is just the story of one of those photons. And eventually it gets captured by one of our satellite experiments, for example. So that is, that's the light that we're measuring. And this radiation fills up the entire universe. And for the first time, it was detected in 1965 by Penzias and Wilson as an isotropic radio background. They were using a radio telescope, and they found that there was like a faint hum, from the sky.
Right here in New Jersey.
Right, that's right. And they measured the temperature of this radiation, and they found that it was extremely cold. It was close to 3 Kelvin, right? So it's this faint background, extremely cold radiation. This is actually, this is what we call the cosmic microwave background radiation. It comes from when the universe is extremely young, hot and dense. And this is one of the hallmarks of Big Bang Theory. This is proving that if you expected at some point the universe is hot and dense enough that you had 3,000 Kelvin radiation that eventually came out of these neutral atoms forming as the universe expanded and cooled, we detected today with a certain temperature. So that's telling you that the universe was hot and dense in the past. This is just another way of looking at the proving that the universe is expanding instead of using galaxies, for example. And later on, the COBE satellite, which is actually showing this, this map of essentially just the smooth background, was measured by the COBE satellite in 1992. So how do we get a redshift from this? So I mentioned that you can think of redshift as this light stretching factor. It's how much the universe has expanded. So you can calculate what the temperature of that radiation should have been when it went from this transition from ionized plasma to neutral hydrogens, and then the photons got emitted. That comes out around 3,000 Kelvin. Then you can just divide that by the temperature that you actually measure today, and that tells you how much the universe has expanded. That gives you an idea. That gives you a rough estimate of what the redshift that the CMB photons are coming from is. So this redshift is actually very well measured. If you do a more precise calculation, more precise measurements, you can pin down this redshift of the CMB very well. Similar to how you can very easily measure the redshifts of galaxies and supernovae using spectral measurements. So we got one piece of puzzle in order to get to an expansion between CMB. How do we measure a distance to the CMB? So to measure the distance to the CMB, we kind of look at this background radiation a little bit more carefully. You build more sensitive instruments, and you try to look extremely close and extremely precisely at the CMB. And then you'll actually find that the CMB it's only mostly smooth. It's, I showed the smooth background. But underneath the CMB, there's actually, underneath this 3 Kelvin background, there's 1 in 10 to the 5 parts of blobs, overdensities and underdensities of the CMB. It effectively maps out, gives you a baby picture of the universe. And the idea here is to measure these blobs in the CMB and use the blob size to measure the distance. And that's what I'm going to talk about next. But first, let's try to understand why the CMB is not perfectly smooth. to understand that, we have to go back to this picture again, this ionized plasma. Early in the universe, at redshift of 1000, everything was extremely hot, like, as I mentioned. And the ingredients that we have in this soup, this cosmic soup that's extremely hot, are three things mainly. The first is a large fraction of dark matter. This is matter that doesn't constitute, the ordinary stuff around us is not made up of dark matter. Most of the universe is made up of dark matter. These are uncharged particles, probably, and they're extremely slow and sluggish. Then you have photons. These are the photons that eventually you see with the CME light. They're hot radiation. And then you have what we call baryons, which are just the ordinary matter in the universe that makes up stars, planets, people, planets, etc. Right? And this stuff is charged when it's ionized, and that's where the universe starts out as a hot ionized plasma that consists of baryons, photons, and dark matter. So what happens inside this fluid, inside this soup of baryons, dark matter, and photons, is that the dark matter, because it's so heavy, makes these large regions of concentrated dark matter just fall in. And because it's making this region where there's so much matter, it attracts everything into it. And so if you imagine there being a large concentration of dark matter in this region, it pulls in all of the other stuff into it. So it pulls in the baryons and the photons. But once the baryons and the photons start getting mushed up together, they develop pressure. Because these particles are charged, they start repelling each other. And so you have this a fight, an interaction between the pressure of the baryon photon fluid and which is trying to make it push it apart. And then you have gravity, which is trying to pull it together. And what it ends up doing is that this fluid just ends up slushing it back and forth around these low densities. So these oscillations get set up in the fluid. But when the universe goes from hot to cold, the constituents of baryons become neutral, and these oscillations stop and get frozen. So here's one way to see this. If you imagine throwing a pebble into a pool, that's showing you how these pressure waves are set up, these sound waves are set up inside the fluid. But imagine throwing many pebbles, and these are regions of many different overdensities and underdensities. They all interact, and all these waves, due to pressure waves, interact, and then they form this very not smooth texture that we see eventually in the CME, right? So these oscillations, the oscillations in the fluid early in the universe, you can think of them as setting up waves. And then you can think of these oscillations happening in many different places, and then they eventually get frozen, and you see this texture. Okay. So this is a picture that was taken by a satellite that went up during the 2000s, called WMAP, which measured the CMD temperature really low. And underneath that 3 Kelvin background, so initially the Kobe experiment had seen some hints of this anisotropy, as we call it, these fluctuations, these bumps. The WMAP experiment measured it even better and saw these bumps and blowups at much higher resolution. And then the Planck experiment, which just released their final data yesterday, has an unprecedented, amazingly accurate measurement of the sky of the CME photons. And what you have to think about this is as a snapshot, a picture of what the universe looked like when it was just about 300,000 years old. And that was like 13.5 billion years ago. And it's showing you these oscillations, these fluctuations that are set up. Now, the idea that we want to use to measure the distance to this CME, we know the redshift, is to take these different blobs, right? You see there's a typical size that these different blobs have. You can take that blob, and if you know what the ingredients of the cosmic soup are, you can predict how big these pressure waves should be. You can predict the wavelength of these pressure waves. So in order to do that, you need to know what the dark matter content is, you need to know how much baryons there are. If you know those things, then you actually have a standard ruler, as opposed to a standard candle, that tells you how big these fluctuations were in the universe when that was happening. And what we do now is we look at the sky and then we measure the angle of these blobs. we measure what angle this blob subtends on the sky. And from simple trigonometry, you can tell if something is the same size and farther away, then you measure a smaller angle. So you can relate, you can get the distance that the CMB photons are coming from just by measuring the angle of these blobs, which you get from these satellite experiments. And you know, taking a ratio of that with the physical size of these fluctuations that you think it should be. And when you do that, you get an answer of roughly 13.5 gigaparsecs, an extremely large distance. Okay, so now you've got this distance to the CMB and you've got the redshift to the CMB. In order to connect that to the expansion rate, it's not so simple as just taking a ratio in the way that you're connecting them to velocity that Sarah will talk about. What you're actually doing is like bringing back this picture of the history of the universe. As I mentioned, is you're measuring the D and Z, the distance and the redshift of the CMB of a very long time ago. And during this time, a lot of different things happened. During this time, the expansion rate of the universe has changed. So you have to take this D and Z, and then you have to sum over and think about summing over this large period of time in order to connect it to the expansion rate that we actually measure today. And that's what these experiments do. That's what the Planck experiment did, is to measure this D and Z from the CMB and then infer what the expansion rate today should be by having some model for how this evolves through the time. And as Sarah mentioned, the Planck satellite just released their final results yesterday, and they get this number to be 67.4 with a really tight error bar, which seems to be in significant tension, right? So here's another plot showing similar to what we talked about earlier. These are measurements from the CMB by looking at the blob size and getting the redshift from the temperature. WMAP measured something that was around 70. WMAP was a precursor satellite experiment measured the CMB, and Planck has measurements around 67. And here are some supernova measurements that, again, to show you that within these, given these uncertainties, are so extremely discrepant. And as was mentioned earlier, because of the fact that you're actually measuring this something that's at extremely high redshift, you're inferring what the expansion rate today is from measurements that were made extremely early in time. They're not local. And so the things that happen in between during this entire evolution of the universe, maybe there's some new particle that affects the fluctuation that we haven't accounted for. These are the kind of things that could account for possible, for the reason why these measurements are disappearing. What do we do from here? So one of the things we can do is to look at the CMB at different scales and build different experiments. One possibility is that Planck, because you can see that WMAP, although it has a measurement that's consistent with what Planck has measured, its previous experiment is actually measuring something closer to what the supernova experiments are measuring. So I work with the Atacama Cosmology telescope. So instead of building experiments that go into space, we go to regions of the Earth where there's very little water vapor, where there's as little atmosphere as we can possibly get to, because microwaves, microwaves are the radiation we're trying to measure, and the reason your microwave oven works is because it heats up water molecules, right? So if you want to measure microwaves that come from space, you want as little water to be there between your telescope and the sky. So that's why we go to places like the Atacama Desert and go extremely, 18,000 feet high, and then collect the same CMB photons, the same light that these other experiments are measuring. And we're currently in the process of analyzing our data to get an independent measurement. So we'll look at the same sky, we'll look at the same CMB, and we'll go through the same process where we have different sets of data with different people analyzing it, and then we'll have an independent measurement based on, and we hope to see whether this is going to give you something that's confirming Planck, or whether it's something that's going to confirm the supernova experiments. And this is just a picture of our collaboration. So if you want to think about doing this kind of stuff in the future, I just want to remind you it's a lot of fun. You get to travel to beautiful places and work with amazing people. This is me at the site in 2013. Yeah, so it's a lot of fun. So to summarize, we get the distance to the CMB from the size of the blobs that we have, that we measure in the CMB experiments. And we get the redshift from the temperature that we measured today combined with an estimate of what we think the temperature should have been when the CMB is formed. And our best measurements of the CMB so far from Plum tell us that this expansion rate is something like 67.4, and it's, it's very descriptive with measurements from other probes. And what we need to do in the future is to measure the same parameter with a different experiment, like the Cosmology telescope, and also continuously think about new physics that could cause tension. And also number 3 that I put up there is to think about other ways, apart from supernovae and from the CMB, to measure the same constant, and that's what Matt's going to talk about next. Thank you.
Time again for a couple of questions.
I feel your definition of blob was a little squishy.
Yeah.
I mean, I could look at that picture and come up with a completely different blob.
Absolutely. Yeah. So what we actually do in the data is to take, so there's a systematic way. So the blobs are, like you said, they're extremely a vague definition, but there's a certain statistic that you can calculate. You can take this map and you can ask the question, what is a number that tells me how large is the power in this map? So basically, how much does this map fluctuate? Okay, and I can get that estimate for how much fluctuation, how much variance there is in this map as a function of blob size. Okay, so that's what I've shown here. Essentially, there's a very systematic and quantitative way of asking the question. What is the typical blob size? You get that from making a plot of something with the CMB experiment was called the power spectrum, and the power spectrum requires you to it gives you a way of characterizing what the power is at a different scales. And what we then measure from there is that most of the power is at roughly half a degree. And that, or half a degree or 0.6 degree, you can get a very tight measurement of where the power is coming from, 0.6 degree. That's actually what we measure and use. This is kind of it's not exactly the way we do. Yes. Sorry, sir.
I have a question. Does your experiment take into consideration things like constructive and destructive interference of the cosmic background?
Yeah, absolutely. So this picture here, which shows you that if you have so if you have one region where there's a lot of fluctuations, right? So that sets up some pressure waves. But if you have many regions, then they construct and construct and destruct each other. The waves interfere. The thing that you eventually end up measuring is the sum which could be could be adding constructively or could be adding destructively. Which is why you not only have blobs that are red, you also have blobs that are blue. Right? Those are regions where things cancel out as much as possible, and you end up having underdensity. So the typical blob size is either red or it comes from either red or blue.
Okay, one more. Somebody hasn't asked a question yet. Okay.
So what does the function h of t represent?
Okay, so that's a great question. The h naught that we're thinking of, right, that we're talking about, the 0 refers to today. It refers to what the expansion rate is today. But under general relativity, when you actually look at the entire universe over large periods of time, the expansion rate actually changes as a function of time. So depending on, so here, for example, you can see the expansion rate in this period that might be, may or may not have existed because of inflation. The expansion rate was extremely rapid, exponential expansion. And then the expansion slowed down, and the universe was expanding slowly. And then later on, h of t became faster. It picked up pace because of this dark energy, the acceleration.
If we have a formula for h of t, then why would we need to take measurements with this d and this d?
So that's a great question. So the formula for h of t ultimately ends up having those omegas and those H naughts. So the omegas and the H naught are free parameters in the HFT. So the thing that you can actually measure, the kind of probes that, Saros was talking about supernovae, I was talking about the CMB, these things measure different combinations of these omega M's and H naughts. So you can write down a model for the HFT, but it still has unknown variables in it. And that's what you try to measure it from.
One thing you learned tonight is the Hubble constant is not constant. Physicists aren't very good at naming things. So our next speaker, our last speaker, is going to be Matt Buckley. As I said, he studies cool dark matter, but he's going to tell us tonight about another technique for measuring the Hubble constant. Hasn't been used yet, but very soon it's going to come into play, and that's the exciting development of gravitational wave detection that I'm sure you all have heard about in the past few years. So Matt's going to tell us how that's going to be done.
Is this on? Okay. So, as we've heard, we have a bunch of different ways of measuring the expansion rate of the universe. One kind of the local volume, which only hundreds of millions of light years, and then the distant universe, billions, tens of billions of light years. And I'm going to tell you about a method that has actually been used exactly once. Hopefully going to be measuring it, using it a lot more in the next decade. And it's called a standard siren. And the reason for that is that what Professor Jha actually was telling you about was sometimes called a standard candle, right? If you have a supernova going off, you know more or less how bright it is. And so if it's an object that you know how bright it is, and you then measure how bright it appears to your eye, you can figure out how far away it is. Standard candle, so you know the distance. What Matt was saying was a standard ruler. You know how big the blob is, and so you see how much of your vision it takes up, and you can tell how far away it is, right? Because you know how big it is, and you can figure out how far away it is when you see it on your field of view. What I'm going to tell you about is a standard siren. It's sort of, you know how loud it should be, in a certain sense, and therefore when you listen for it in the right way, you can tell how far away it is. But what it is looking at neutron star mergers. There was a really incredible discovery in 2017 that we'll have to talk about because we're going to have to take a little detour from the physics and astronomy we've been talking before to explain what on earth this measurement is. I'm going to skip through these relatively quickly because you've already seen exactly the slide. We're looking for velocity, the function of distance. We need this Hubble parameter. So, we want to measure for some distance away, we want to measure the redshift or the velocity for some objects. And I'm going to be talking about something that's kind of a local universe measurement. So it overlaps with the supernova measurements, less so than the CMB. We already saw redshift. This is actually absorption lines, right? You guys saw emission lines. Right? When we look here. But if you send light through something that has some chemical element in it, those lines will get absorbed. So you have some unshifted lines, but if you look very carefully here, each one of these lines will be shifted to the red, and that tells you that something is moving away from you, right? And the thing to keep in mind is that each of these methods we have of measuring redshift and distance, right, has the potential for what we might call systematic errors. So a statistical error is you measure a bunch of things a bunch of times, but you have only a limited data set. And maybe you just got unlucky, right? And so your answer is sort of statistically limited. But your other possibility is that you have a systematic error. You've made some mistake, not intentionally obviously, but you made some mistake on how you're doing your measurement, and that is just shifting your answer over by a little bit. And so the question is, are these two measurements that we've heard about how to measure the Hubble parameter, are there some secret systematic error that we didn't know about that would actually make them agree, because we made that mistake, we don't know, we think they disagree. And so one solution, or one way to do it, is to go back and be very careful and make sure you didn't make a systematic error. The other thing you can do is say, okay, I have two answers, they disagree, let me find a third answer, and hopefully that will agree with one of them. and tell me what's really going on. So let's find this new distance measure. So I have to tell you about neutron-star mergers. What are they, and how do we detect them? To tell you how we detect them, I need to introduce gravitational waves, which means I'm going to be telling you everything you need to know about general relativity, which we all know is a very simple topic, and I'm going to cover it in one slide, and it'll be perfectly understandable after that. And after I introduce gravity, I can tell you about gravitational waves, and then I can finally, at the very end, tell you about what these neutron-star mergers and their gravitational waves tell you about the expansion of the universe and the idea of the standard siren. So we're taking a little bit of a tour through some fun physics. So what are neutron stars? Well, we actually heard about white dwarfs, right, way back at the beginning when we were talking about this white dwarf supernova. So white dwarf supernova come from a white dwarf, which is one possible end state for stars. If you have a bigger star, when it explodes, it leaves behind a corpse, right? And that corpse is so massive that it cannot sustain itself with electrons separated from protons. There's actually just not enough room inside this relic of a massive star to fit all of the electrons. And so the electrons are forced to combine with the protons and they become neutrons. And so you're left with a ball of neutrons that is about the mass of the sun and it's about 10 kilometers in radius. So, fits into a small or reasonable sized city. Right? Here's a picture of a neutron star sitting, next to Manhattan. Now, we've known about these things for a long time. They have very powerful magnetic fields. They're still spinning. Sometimes they have a jet of energy that's coming off one of their spin axes or their magnetic field axes, and that's called a pulsar. Right? So this is actually a picture of a cloud of gas in space, and you can see there's pulsations going on. That's a pulsar spinning, and it's dumping energy back into the system. You can actually see the pulses of energy coming off of it. So a neutron star by itself, if you're not lucky enough to be living in a way that you can see that pulse of energy coming right at you, is basically pretty invisible. Right? It's 10 kilometers across. It's not giving off a lot of energy. It's just floating in space. And so it's hard to see. But sometimes neutron stars can end up in binary systems, a neutron star orbiting another star. If that star is a kind of regular star, like our sun or a bigger star, it can get close enough to start stripping gas off of the outer layers,